Hi, everyone. We're going to get started in about 1 minute. So just want to let everyone know so we can keep to our schedule. Okay, welcome everyone. We have great attendance today. We're very excited. I'm Judith Shankman. Adi, can everyone hear me? Hopefully, okay. Wave. I'm Judith Shankman. I'm the Midwest Regional Director of American Friends of Hebrew University. Thank you for joining us today for our webinar. AFHU connects the passions of Americans with the talents of the Hebrew University of Jerusalem, one of the most distinguished academic research institutions. In addition to raising awareness and funds for the university, AFHU helps the university retain and recruit outstanding faculty, build teaching and research facilities, and provide scholarship and fellowships for students. AFHU's support helps the university advance human understanding in a myriad of fields, including agriculture, astronomy, nanotechnology, energy, veterinary medicine, and much, much more. During these challenging days, there are many ways that you can get involved with us, from participating in future webinars, learning about groundbreaking research currently going on at Hebrew University, to supporting research and scholarships at the Hebrew University. Please visit afhu.org regularly for information about our future programming and webinar. And we currently have a whole series of webinars on a variety of topics that we are all looking for while we're sheltering in place and looking for enriching and informative programming that is food for our soul and our intellect. So today we're going to be looking forward to an illuminating discussion about global climate change and water resources, which is a topic that touches and concerns us all. To submit a question, there's a box at the bottom, a Q&A box, and please submit them. And at the end of Adi's presentation, we will try to answer as many as possible. Now I'm pleased to introduce Professor Adi Torfstein. He is an associate professor at the Institute of Earth Science at the Hebrew University and at the Inter-University Institute for Marine Sciences of Eilat. He's a geologist, a geochemist, an oceanographer. The objective of his research is to reconstruct past climate changes and study mechanisms driving them to better understand current and future global climate change. Professor Torfstein uses field observations together with chemical analysis to reconstruct the history of the Dead Sea, the Red Sea, and the Weddell Sea in Antarctica over the last hundreds of thousands of years, and studies the source of dust and how climate change controls its transport modes and pathways. The objective of the research is to understand the past and to apply it in evaluating potential future climate change trends. Adi, the floor is yours. Thank you.
Thank you. Thank you, Judith. And I'd like to say thank you to Miriam and Lori and Marsha as well. And thank you for joining in to listen to me today. So before I begin, I was asked to say a few words about myself. So who am I? I was born and raised in Jerusalem. I did my undergrad and graduate studies at the Hebrew University, moved on to Columbia University for a postdoc and stayed on for a couple of more years there until I returned in 2013 to the Hebrew University. where I started a joint position at the Institute of Earth Sciences and Inter-University Institute in Eilat, as Judith mentioned. I'm actually currently in Santa Cruz on sabbatical. That's my background. In terms of research fields, as Judith said, I use geochemistry, the chemical composition of seawater, of sediments, in order to better understand processes in the oceans. So that's my oceanographic side. I use all of that together in order to reconstruct and better understand climate processes in the past and in the future, or in the present towards the future. My main focuses geographically are in the Red Sea, Dead Sea, Mediterranean, and that highlights my interest in climate change across the Sahara Desert. And I also work somewhat in Antarctica. Again, looking at modern processes in order to better understand and reconstruct the past history of climate on Earth. And in Eilat, those of you who have been there, you can see this is the Gulf of Eilat. This is the underwater observatory, and my lab is actually located here. So what we do in Eilat is to use the unique features of this sea, the northern part of the Red Sea, in order to reconstruct or study processes in the ocean today, such as plankton dynamics, dust impacts on the ocean, the composition of sediments and seawater, and so on and so on. And because of the unique features of the water, the seawater in Eilat, we use this study in order to be able to say something about processes in the middle of open oceans. For example, the middle of the Pacific Ocean, which is not accessible. We make process studies in this environment. And all of these studies together, which include students and multiple cruises every year, these are all under the title of REDMAST, which is the Red Sea Dust, Marine Particulates, and Seawater Time Series. Again, looking at the modern environment in order to reconstruct the past and be able to say something about future patterns of climate change, oceans, and so on. So that's the introduction. I want to move now towards the talk itself, titled, just let me move this aside, Global Climate Change and Water Availability from the Past to the Future. So this first slide shows us the distribution of water on Earth today. And as you can see, most of it is in seawater. 97.5% of all water on Earth today is seawater, salt water. Only 2.5% of the water is fresh water, but out of that, only a fraction is available as fresh water. Only 0.01% is usable for human societies, agriculture, and so on as fresh water. And what pops to mind now is the question of how global warming, which is this term we all hear about on the news, how this process of global warming will affect this number. Will it become larger or smaller in future? So these are important questions, and they used to dominate the news before COVID-19. So for example, in this front page of the New York Times from February 2020, only a short while ago, a news bit about the struggle on the resources of the Nile water between Egypt, Sudan, and Ethiopia. So this fresh water is the lifeline for Northeast Africa, and changes in its availability will of course cause some serious geopolitical instability. We know in California, there's issues of droughts, of course in the Middle East, in South Africa. This is the front page of Science, the leading on the left, on the right bottom hand side of your screen. The front page of Science last week, the issue was dedicated to drought under global warming. So this is a really important and hot topic. But before we begin, we want to understand what is this term of global warming. So it's defined strictly as the increase in Earth's average temperature. And if we look at the record of global temperatures since 1960, down here, moving forward to 2017, and this is global temperature increases above background values, above the pre-industrial average values, we can see that today, or in 2017, when the IPCC, the Intergovernmental Panel on Climate Change, produced this diagram, temperatures were 1 degree Celsius above background values. And extrapolating forward, This value is predicted to reach within 20, 30 years. We have quite a lot of uncertainties here, but we're predicted to reach 1.5 degrees Celsius above pre-industrial values within a really short time. And that might have serious implications to the global climate. It raises many questions. First of all, is this a real global warming? Is it natural? Maybe it's just part of a natural cycle, so we don't have to fuss about it. How does this relate to past climate changes over long time periods? And even if it is warming, if it is true, why do we care? Why does it matter? How will Earth respond? And I think from a scientific point of view, or at least from my point of view, it's really interesting to think about the question, how do we in fact know all of this? How do we know what past climate looked like? And this is something I want to focus on in this talk, and we'll get to this in a minute. How will global warming change Earth? So we know it's likely to change climate, weather, cause rising sea levels. This in turn will impact ecosystems and of course impact people, impact society. As a logical sequence of things, if we think about global warming, it will probably cause increased melting of polar ice, which in turn will increase sea levels. Sea levels are predicted to rise by 1 meter within 80 years by 2100. So that's a lot of sea level rise. This will cause a lot of things: displacement of coastal communities, flooding of coastal ecosystems, groundwater, which is currently used for drinking water, will be salinized. So that's a big issue. Climate change or global warming will of course cause changes in precipitation patterns. Some areas might experience droughts, others might experience floods or extreme weather. And all in all of these changes, and there's many more of them, which I won't go into, will have implications on society. Loss of food security, less economic activity, geopolitical instability. I gave the example of East Africa. The Middle East is another example. We can think of a few more. Perhaps waterborne diseases will increase due to this change. And of course, we might have a situation of far less clean water available for human society. And again, the list goes on, but these are really serious implications. And I want to go back to the basics and think about actually climate. And to begin with the question, we know that we've seen that temperatures are rising over the last century. And the question is, will this cause in future Earth to be wetter or drier? This is a big question. Hang on. This is a big question, and you can see the different colors on this satellite image: the yellow deserts, the green tropical zones, and northern zones. And the question is, will these colors, will these climate zones change geographically over time? Now we know that in the past, Earth's climate was significantly different than today. And probably the most striking example of this is actually not warming, but cooling. The last glacial cycle Earth went through, and this is a diagram depicting Earth 25,000 years ago, when Earth was in the midst of an ice age. We call this a glacial stage. And you can see that Earth was quite different. Polar ice was significantly expanded relative to today. Canada was covered in ice. Sea ice locked in the North Atlantic. Europe was covered in ice. So were large parts of Siberia, the Tibetan Plateau, the Andes, and of course expanded sea ice in Antarctica. So these are big differences. But if we zoom in, we also know that the ice is water. And water that formed these large ice sheets had to come from somewhere. And this somewhere is the oceans. So in fact, the expansion of ice sheets caused the decline in ocean water levels. And we can see this nicely if we look here north of Australia, in Indonesia. Expanded or much larger land masses are exposed to the atmosphere compared to today because of the decline of sea level. The same goes for the Caribbean Sea and other places. And this, of course, impacts the composition of water, the composition of the atmosphere, and so on and so on. So I think it's quite intuitive to understand the connection between temperature and sea level But again, we're still stuck with the question of, back in the glacial, was there more or was there less precipitation? We don't know. It's not so intuitive to understand these changes. Going back to today's satellite image, if I just broadly mark the desert zones, the desert bands in the northern hemisphere, that includes the West USA, Sahara, Arabia, and parts of Tibet. And looking at the south, looking at the Andes, South Africa, and Australia, we see these two desert bands north of the wet equatorial. What controls this? Why should there be any change, any difference in precipitation around the world? Why isn't it all the same? So the question is, what controls, what's the fundamental process that controls climate on Earth? And the answer is this. This is the sun. The radiation from the sun controls, to a first order, is the most important controller of climate on Earth. And when we think about it, the difference in temperatures between night and day, it depends where we're located, but differences of 10, 15, 20 degrees Celsius, these differences are equal or much larger than the whole glacial, interglacial, ice age and non-ice age differences. So that's a big difference. That's the radiation from the sun makes a big difference and controls a lot of the story we're going to tell. This is a schematic diagram of Earth, and we can see the sun rays, the sun radiation hitting Earth. Most of the radiation, or more radiation, is received by the center of the Earth, the equator, the subequatorial areas, and we know that these areas are warmer compared to the poles, which receive far less radiation. But even as a schematic diagram, this diagram is a bit incomplete, because we know that the axis of Earth, the axis of Earth's rotation around itself, is tilted, as depicted here. And once it's tilted, we can also see that the story is slightly more complicated. In this case, we're looking at a scenario of more radiation reaching the northern hemisphere compared to less radiation reaching the southern hemisphere. And this is a situation of summer in the northern hemisphere and winter in the southern hemisphere. When the axis tilts again, now we're looking at summer in the southern hemisphere compared to winter in the northern hemisphere. So we see here a tight control between the radiation of the sun and the geometry of Earth's position. And just think about the situation of this axis. If this axis was tilted more or tilted less, that might make a big difference to the total radiation distribution of the sun's energy onto Earth. For example, if it was tilted more, we'd expect a warmer summer, in this case in the southern hemisphere, and a colder winter, and vice versa. In fact, when we go back in time, we know that Earth's tilt, this axis tilt, did in fact change over time. And we see this in this nice cartoon. And the tilt isn't big. An average tilt of about 24% degrees changed over time by 1 or 2%. So it's not a big difference, but it does make some difference to the radiation. And you can use this red arrow as a marker of the radiation. You can see that these small tilts do make a difference to the total distribution of radiation. And these changes in the tilt took place or changed over a cycle of 41,000 years back in time. Now, this isn't the only difference. We also know that this tilt isn't stable. It's what we call wobbly or precession. And it's not only that the total tilt changed, its stability was also different over time. And again, if you use the red arrow here as a marker, you can see how the radiation changes to different parts of the world. Now the North Pole receives a lot of radiation and now less, and so on and so on. Another cause for changes in the radiation of the sun towards Earth is the total distance of Earth from the sun. So now, for example, now the Earth was distant from the sun and now it's closer. And this cycle of changes of the total distance of Earth from the sun at a frequency of about 100,000 years imposes another component that dictates the total radiation, solar radiation from the sun onto Earth. I'll say as a side note that this 100,000 year cycle is more complicated than we're seeing here, but it doesn't matter for now. To sum this up, all these orbital parameters can be calculated and actually have been calculated, and we can calculate the total solar radiation, which we call insolation, that reaches the surface of Earth. And this insolation is dictated by the Earth's rotation axis, its orbit around the sun, and this all changes in time. We call these cycles Milankovitch cycles, and they're exemplified here in this diagram showing the last 150,000 years versus the solar insolation. And you see these cycles going up and down, warmer, cooler, and so on and so on. And just to give you an example, we know that just over 20,000 years ago, Earth went through this last glacial cycle, the last glacial maximum, when insolation was low, compared to a time of 130,000 years ago, when Earth was warmer, even warmer than today. This is a time we call the last interglacial maximum. You'll also notice there's additional cycles here, and I'll get to that in a minute. So let's compare those additional cycles to sea level, okay? So in blue here, we're looking at sea levels from zero, from today, down to lower sea levels. And we're looking at a range of 600,000 years before present. And we can see that sea level went up and down, and so on and so on. And if you look closely, you can see that these variations in seawater, in sea levels, comply or correspond quite nicely to insolation values, the radiation of the sun, plotted here in gray, and you can see this here. I hope you can see my marker plotted here. So high sea levels, high insolation, going down, going back up, and so on and so on. And indeed, during the last glacial maximum, about 20,000 years ago, when Earth was cold, sea levels were 120 meters below current sea levels. So that's a big difference. Now let's look at temperatures and carbon dioxide. These are two important components, which I'm sure you've all heard of, carbon dioxide, I mean. And if we look at temperature, for example, so once insolation is high, we see that temperatures are increased 130,000 years ago. This is what I call the last interglacial maximum. And then temperatures drop until a minimum 20,000 years ago, the last glacial maximum. Earth is cold, polar ice is expanded, sea level is low. How does this reflect on carbon dioxide? Carbon dioxide shows similar patterns, high during warm phases and low during cold phases, but it's not entirely tuned to these insolation cycles. I think you can see this quite nicely. So before we talk about that, let's think about what is carbon dioxide, plotted here as ppm, parts per million. And this brings us to this term of greenhouse gases or greenhouse effect. So I said that the sun energy, the sun radiation onto Earth is a really important player in modulating global climate. However, a lot of this radiation is emitted back out into space. So not all of it is absorbed on Earth. It's emitted back into space unless the atmosphere is thick enough and enriched enough in various molecules or gases which can absorb this radiation. And we call these gases, as for an example, carbon dioxide, we call these gases greenhouse gases because they absorb this energy, and hence the energy or the temperatures or the warmth is maintained within the atmosphere, and the atmosphere temperature increases. So the more carbon dioxide we have in the atmosphere, the more we tend to keep in the sun radiation and temperatures increase. So thinking about this logically, solar energy shifts temperatures on Earth up. Temperature can cause a release of carbon dioxide into the atmosphere. And I'm not going to go into the details here, but you can just think about changes in the distribution of forests and carbon dioxide maintained within the oceans. Once temperatures go up, carbon dioxide and other greenhouse gases are emitted into the atmosphere, their concentration goes up, and hence we have a positive feedback, which in turn kicks up or boosts in, and temperatures increase again. So this is an internal cycle which takes temperatures up. The end result of this process is that polar ice can melt, sea levels go up. We see a range of changes on Earth, climate, ecological changes, whatever, including changes in rain patterns, which we haven't talked about yet. But if we look again at this diagram, we're looking at sea levels, temperatures, and carbon dioxide versus insolation over the last 600,000 years. And this is a complicated diagram with many, many small details. So we don't want to dwell on this, but what we do want to look at here and take from this slide is the fact that we know what the rules of the game are. The rules of the game are that insolation, sun's radiation, can be calculated and is cyclistic over time and imposes similar cycles of natural processes, of sea level changes, temperature, and so on over time. So in fact, we can go back to any point in time over the last 1 or 2 million years, and based on the theoretical calculation of insolation values, we can know whether this is a glacial or an interglacial, and geological evidence, in fact, supports this. And we know that over the last 600,000 years, and actually even more than that, Earth went through these continuous cycles of glacial and interglacial, warm and cold, warm and cold, warm and cold. So we know what the rules of the game are. So that's what we want to take from this slide. Now, going back to this diagram and the question of, is Earth going to become wetter or drier? Again, the connection of temperature and sea level and ice seems to be intuitively understandable. But what about precipitation, rain? That's less intuitively taken out of this slide that we're looking at. So in that case, we want to turn to other paleoclimatic archives, and we know of many archives that can be used. These are some examples. In many cases, people extract, core out sediments from the bottom of the oceans, deep sea sediments, and this is an example of a sequence of cores. And without going into details, it's clear that different colors here, for example, the dark black here compared to the light brown, these sediments accumulated over time in the bottom of the oceans, and the differences in color tell us something about changing conditions of the oceans. What these differences are doesn't matter at this point, but we can use these differences to reconstruct the past conditions in the oceans and Earth's climate. The same can be done using cave deposits and ice cores. For example, coring out ice cores in Greenland or Antarctica, and these ice cores look like this. We can really get a high resolution record of climate in the past. And what's nice about ice cores is that as the ice accumulates, for example, in Greenland, it also locks within it small bubbles of air. Bubbles of air which actually record the atmospheric composition at the time of deposition. Now, once we take out this ice core and take it to the lab, we can melt slowly and gradually each layer of ice. And this melting releases out the small locked-in air bubbles in these ice cores. And we can measure the composition of carbon dioxide, for example, in the atmosphere 20,000 or 50,000 or 1 million years ago. So this is one of the things we do, or people do with ice cores. Other efforts are focused on tree rings. And as I said, there are many ways to reconstruct past climate. But what's unique about the pictures we're looking at now in this slide is that none of them provide a direct interpretation or direct story or record of precipitation. In all cases, we have to measure, for example, the deep sea sediments, measure the composition of the sediments, and interpret the composition in terms of more or less wetness. So there's no direct record here for precipitation. But this is not the case when we talk about lake deposits. Lake deposits provide us with a direct record of past hydrology, of past precipitation, and this isn't the case for all lakes. We need to choose carefully the lakes. They have to comply to several parameters, but generally speaking, when we have a region or a basin, a continental basin with more rain, lakes in that region tend to display an increase in lake levels, and vice versa. During droughts, less rain, lake levels drop. Another advantage about these lakes is that they're located in continental settings, so the records they provide are much more relevant to human society. For example, I'll talk in a minute about the Dead Sea. So the Dead Sea really records climate and hydrology in a region where people need to know about it, compared to, for example, Antarctica, where people don't live. So these are also additional advantages of using lake deposits to reconstruct past hydrological patterns. As I said, I want to take you to an excursion to the Dead Sea, just to give you a feeling to how we actually get to these lake levels in the past, how do we reconstruct them, and what do we do with them. So we're going now to the Dead Sea, and this is a slide looking from south to north. The Dead Sea, of course, is in the middle of the slide, the Negev Desert in the south, the Sea of Galilee, the Kinneret up here. And before we move on, just pay attention to the difference in colors, okay? We're looking at a desert, the Negev Desert, the Jordanian Desert are yellow, desert-like, compared to the green regions in North Israel and Lebanon, which have more precipitation. And there's a sharp boundary between these two climate bands. And when people talk about global warming and global climate change, as I said in the beginning, we now hit a 1 degree Celsius increase above background levels, and that might sound negligible, not a big deal. But that 1 degree Celsius increase might also translate in this case to a change, a small change in the distribution of green versus yellow. It doesn't have to be big if we're talking about the global perspective. But it's enough that this green-yellow boundary moves 50 kilometers north or south that millions of people will be impacted by this change. This small change globally, but huge change locally. And of course, Israel is not the only place to be exposed to these transitions. The same happens over the entire world. So many, many millions of people are sensitive to these global climate patterns. But going back to the topic now, I want to talk about Dead Sea levels. This is a picture of the western margins of the Dead Sea. We're looking from the Dead Sea towards the west. This is Kibbutz En Gedi, if anyone has been there. And in the past, we know that the Dead Sea water levels were much higher than today. For example, 25,000 years ago, water levels were 160 meters below sea level. Okay, we know that the Dead Sea is the lowest point on Earth, and hence the minus here, but water levels were much higher than today. And in fact, Kibbutz En Gedi at the time would have been completely flooded by the past cycle of the Dead Sea. By 6,000 years ago, water levels of this lake had receded to 370 meters below sea level. And this decline in water levels continues until today. In 1997, water levels were 413 meters below sea level. And you can see the pier that was built by Kibbutz En Gedi then, today it's abandoned. By 2008, only 11 years after that, water levels were 421 meters below sea level. They built another pier. By the time I prepared this slide, which was, I think, 5 or 6 or maybe 7 years ago, water levels were 424 meters below sea level. So this second pier had to be abandoned. And today, water levels are approximately 431 meters below sea level. So water levels are declining by 1 to 1.5 meters per year. And the lake level is receding significantly. Of course, as water leaves the lake, what's left behind are salts, and the salinity of the Dead Sea is over 350 grams per liter, which allows us, of course, to float in the Dead Sea and read the book, and I think you all know these pictures. But moving on with lake levels, another interesting site is Masada. Many people visit Masada, the really unique archaeological site, and the archaeology is impressive. And if people look from Masada towards the Dead Sea, the view is really significantly impressive. But for geologists, when we stand at the top of Masada and look to the east towards the Dead Sea, what we really like to see are these white, soft, moon-like small hills. And these are the remnants of the past high Dead Sea that existed during the last glacial maximum. And these sediments, these soft, unique sediments, which we can see now from close up, precipitated from the last glacial cycle of the Dead Sea, which we call Lake Lisan. And this white appearance is really unique. And zooming in, we can see here some pictures from field work when we sample these sequences. Zooming even further in, these white sequences are actually not entirely white. They're composed of couplets of brown and white lamina, only 1 or 2 millimeter thick each. And the brown lamina are deposited after winter storms. So winter storms bring in floods, flush in a lot of mud into the Dead Sea, and that precipitates and sinks to the bottom of the Dead Sea as these brown lamina. During summer, the water evaporates, and we get precipitation of aragonite, which is a calcium carbonate mineral that sinks on top of the brown lamina. So these couplets of aragonite and detritus are actually annual precipitation cycles, and we can use that to our advantage. Before we move on, we want to know what the ages are here. If we want to say anything about lake levels, we want to know when they took place. So we need to date this sequence. People over the years have used many methods, radiocarbon dating, uranium thorium dating, and I won't go into the details, it doesn't matter at this point. But they also used varve counting, so counting these couplets of aragonite and detritus over these 40 meters of sediments. That also gives us an age model, an estimate of the timing of each of these layers. In this example, we're looking at the diagram of uranium thorium ages versus elevation in this sequence in Masada. It turns out, accordingly, that the sequence of sediments we're looking at precipitated between 70,000 years before today until about 15 or 10,000 years before present. And the advantage of having such good knowledge of this age, of the age model of this sequence, is that we can then pick out any layer we want. For example, pay attention to this brown layer, which has an age of about 30,000 years. And if we zoom in at it, we know its age, 30,000 years, because of the good dating. But zooming in, we see this is a unique layer. If you look at the bottom part of this picture, we see these aren't these typical white laminated aragonite detritus layers. What we see here are tilted layers, pebbly, coarse, and layers which are really familiar because we see them today along the shores of the modern Dead Sea. These are in fact beach deposits. So we know that 30,000 years ago, the water level was at this elevation based on this picture we see here. After these beach deposits were precipitated, lake levels went back up, and at the same site, we find precipitation of these aragonite lamina, which precipitated from deeper waters. So this is a data point or information we can plot on a lake level curve. Another way to get at past lake levels is to use archaeological and historical data. This is a picture of a Roman anchor which was discovered along the modern shorelines of the Dead Sea, and it's made of wood, and it was dated using radiocarbon to just over 2,000 years ago. And that fits nicely with the fact that we know the Romans were there 2,000 years ago. But this anchor, which was abandoned by the Romans, it was stuck in the sediments, they couldn't take it out, so they just left it there. This tells us that 2,000 years ago, water levels were above the point where this anchor was found. This is another data point we can add to the plot. Looking at the cliffs of the Judean mountains, as we drive along the Dead Sea, we can look up at the cliffs and you can see these straight lines, which I'll highlight now. And these lineaments, these lines, mark past terraces of shorelines. So if we know to date these shorelines, we can add these additional data points to a lake level plot. And this is what I'm showing you here. So this plot shows us time from 70,000 years to present on the bottom axis, and elevation from 160 meters below sea level to 420 meters below sea level. And all these different data points coming from different studies over many years, from different lines of evidence, they can all be used to prepare and plot a lake level curve. And this lake level curve has many interesting features, but for the purpose of the talk today, what we want to note is the clear difference between the average water elevation during what we call the last glacial cycle, 70 to 15,000 years ago. Elevations here were far higher than what we know over the last 10,000 years during the dry, warm period, which we call the current interglacial. So we see here evidence, concrete evidence for the fact that during the last cold glacial, water levels in the Dead Sea were significantly higher, while warming caused lake level decline. So precipitation patterns in this region of the Middle East are that cold indicates more wetness, while warm indicates drying or aridity. This is the Dead Sea, but it's only one lake. Let's move on and look at another site or another region, in this case in the Southwest USA, also a region where droughts and future climate change is a big deal. So we're looking now at the satellite image of California, Nevada. And if we look at Nevada, we can notice many small potholes, I would say, small sort of scrapes in the landscape. And some of them are dry, some of them are still filled with water. This is an example of a lake actually in California, a monolake. But if you look closely, this water body used to be much larger. You can see here that there's evidence, I mean, intuitive evidence that the lake was once larger. And it turns out that during the last glacial, this entire region, which today is on the verge of aridity, was actually much wetter. So we see many lakes here. The Northern Hemisphere polar ice sheet reached all the way across Canada and into what is today the US. And we find many lakes around this region. I just want to focus on two now. I'll take you to Lake Lahontan in Nevada and Lake Estancia in New Mexico. So the lake level curves for both these lakes were reconstructed following the same principles I showed you in the Dead Sea. And lake levels in both cases are quite clear. Over the last 28,000 years, in both cases, we see higher lake levels, both in Lake Lahontan in Nevada and in Lake Estancia in New Mexico, during the cold glacial phase, shifting towards low lake levels, which we interpret to mark arid pulses in this region during the last, let's say, 10,000 years when temperatures rose. So we see a similar pattern in the Dead Sea, in Lake Estancia in New Mexico, a pattern of high stands in the lakes associated with wet and cold conditions compared to low stands during dry and warm phases. But these are only two regions, and the world is big. So we want to look at the bigger compilation of evidence coming out of lakes around the world. And this was performed by McGee just recently. And each of these symbols, the blue and red symbols on this map, mark a lake that was studied around the world. The red symbols mark an association of the specific lake we're talking about, an association between warming and aridity and lake level decline, compared to blue symbols, which mark an impact of warming that causes more wetness, actually, a lake level rise potentially. And we see that the distribution of these colors, the red and blue, isn't random. Of course, in the West USA, we find a strong association between warming, global warming, and aridity, lake level decline. The same goes for the Sahara, the Middle East, possibly the Tibetan Plateau, of course, the Andes down here, South Africa, and so on. It also turns out that there are regions that respond with increased wetness to global warming or to any warming. And these are in Amazonas, Africa, Indonesia. So the tropical band actually seems to tell us that with increased temperatures, precipitation will increase rather than decrease, as is the case in the Southwest USA and the Middle East. So to a first order, the collective observations that people have made around the world, and we can couple this with additional evidence from bottom seafloor sediments and ice cores and so on, but just sticking to the lake records, we find that the wet regions, in this case in the tropics, with global warming will become actually wetter, while dry regions will become drier. Okay, so what I just said about the prediction of wet becoming wetter and dry becoming drier fits nicely to the rules of the game as we established them earlier in the talk: insolation values, sun radiation, cyclicity, glacial interglacial cycles, warm, cold, high, low lake levels. So those are the rules of the game, and we think we know them quite well. However, it turns out that the rules of the game have changed. No one told us about it, but they have changed. And in order to emphasize that, I want to focus now on carbon dioxide, this greenhouse gas, and look at the recent record of carbon dioxide, which I highlighted here. So we're looking at carbon dioxide concentrations in parts per million over the last 30,000 years. And you can see that carbon dioxide went from low values, low concentrations during the last glacial. It rose about 15,000 years ago, rose to the last 10,000 years of warmth, rose to a value of about 280 parts per million. But at the edge of this curve, we can see this blip, this glitch, this somehow mistake in the record. But this, of course, is not a mistake. And this is actually the anthropogenic carbon dioxide increase over the last 100 years. Okay, so this is obviously not going along with the natural cycle of variability of climate, carbon dioxide that we know of over the last 1 million years. So if we know that during cold glacial phases, concentrations were 180 parts per million in the atmosphere, and during warm phases, interglacials, concentrations were 280 ppms, today, and this is actually not today, I checked this value on Sunday when I prepared this slide. So on Sunday, atmospheric concentrations of carbon dioxide were 417 ppms of carbon dioxide in the atmosphere. You can check it for yourself in this link if you want. But this value is almost 50% higher than the highest value measured in the atmosphere during warm phases over the last 1 million years. And this means that the rules of the game have changed. Rather than having this solar insolation cyclicity, we now add in this component of carbon dioxide, which takes the warm phases to an extreme case, an extreme scenario. And we have to consider this change in the rules of the game as we move forward to predict future climate change. And this relates to the questions I started with about global warming and is it natural? I think the evidence is quite clear that the global warming, in this case in temperatures, I didn't plot it, but this goes along nicely with carbon dioxide increases we just saw in the previous slide. And we have to realize that these changes over the last century impose a significant change to the natural variability of climate on Earth. In order to understand that, we have to better understand past climate changes, but now we know that we're in a new stage, a new, if you want, a new frontier in the climate evolution of Earth. And these changes can be modeled. Moving forward, this is a model predicting precipitation at the end of the 21st century. So this is approximately 8 years from today. And the picture here takes into consideration both the observational evidence I showed you coming out of lakes and so on, but also the impact, the potential impact of carbon dioxide in the atmosphere and global temperature changes. And we see that this model fits nicely the observational evidence. So the Southwest USA is going to become more arid. Brown here is arid, less precipitation. The same goes for the Middle East, but the case here, or the model here, predicts a more extreme case. It's not only the Middle East and only the Sahara that will become more arid. We can see here a brown patch migrating all over Europe. And it means that Europe will be exposed to significantly less precipitation in the next or in the coming century. By contrast, there are other regions which will experience more precipitation. This is, for example, in Canada, Scandinavia, and indeed in the tropics, some of the Amazonian region, East Africa, a significant increase in Papua New Guinea, for example. So there are many small details here, but all in all, we know that climate will change and precipitation will change differently in different regions of the world. The last thing I want to say here is that this sort of map doesn't give us the full picture, because there's a big difference between an increase of 20% of precipitation or decrease in precipitation over the annual cycle. There's a big difference between that and taking the entire annual precipitation and dumping it on a certain region over two extreme events, two major rainstorms, for example. That makes a big difference to the ability of us, of the human society, to utilize the fresh water, either by storage or replenishing lakes and so on. Massive rainstorms will eventually translate into a loss of a lot of fresh water as runoff into the sea. So these are all nuances that have to be considered here, and I'm not going to expand on that at this point. So to sum up, the big question we wanted to deal with was what will be the impact of global warming on freshwater availability in the future? And whatever we say about it, we have to remember that the past is a key to understanding the future. We know, based on studies of past climate change, that Earth's climate shifts change between warm interglacials and cold periods, glacials. However, at present, the rules of the game have changed somewhat, and current global warming in magnitude and rate is completely different compared to anything we've seen in the past, which also tells us something about whether it's natural or not. Okay. I talked a bit about examples from lake records, which provide us with direct traces of past hydrological dynamics. And to sum this up, we saw that under global warming, wet regions will become wetter and dry regions will become drier. And we expect that the increase in carbon dioxide and the global warming we're experiencing right now will take this last sentence and make it even more extreme. So with that, I thank you. And if anyone has questions, I'd be happy to answer.
So thanks, Adi. This has been amazing and informative and a little scary. So we had someone emailed a question. Do you want to, you want me to read it and then, or do you want?
Let me find it. Yeah, okay, so I'll take it. So we had the question from P. Ballis, I hope I'm pronouncing it right. And I'll summarize this. So the question was that given that carbon dioxide solubility is inversely proportional to temperature, it's natural that as temperature rises, carbon dioxide will increase. So the question was, can we separate these two phenomena, and can we determine whether one is leading the other? So this is really an important question. And if I phrase it differently, one could ask, based on the evidence we have over the last 1 million years, and we have a lot of evidence, did carbon dioxide records increase before temperature increased into interglacials, into warm phases? And even in the 19th century, do we see first a temperature increase, or do we see first carbon dioxide increase? So the answer is complicated. There's no distinct answer. The reason being that if we take it down to the bottom line, we think that temperature, in terms of processes, temperature is what leads the climate cycle. However, as you saw, there's a positive feedback between the two. So as temperature increases or decreases, it also changes the storage capacity of various pools of carbon on Earth. This could be the oceans, and it could also be the Amazonas forest, so biologic material. It could also be the capacity of the atmosphere to maintain these greenhouse gases. But once temperature changes, it changes the capacity of, let's say, the oceans to maintain the carbon dioxide. We have a release of carbon dioxide to the atmosphere, which has a positive feedback and causes temperature to increase again, and it's an internal cycle. Which one came first? We're talking about really closely coupled processes, so it's not really easy always to distinguish them. And in fact, over time, over geological time, we know that in some cases, carbon dioxide appears to have increased first, while in other cases, it's temperature.
Okay, thank you. So we have one question that's quite long in the Q&A. I'll try to read it and maybe you'll get the gist of it. The IPCC will add polar particles forcing plasma solar winds to its model in 2022. Ice core sampling dating to 70,000 BCE indicate that the sun is a variable star with about 12,000 year nova cycles. The Van Allen radiation belts protect Earth from most particle bombardment, but solar flares can penetrate the shield and induce significant levels of electromagnetic energy in the Earth's crust. The last major, is there a question? Oh, there is a question, sorry. The last major solar flare occurred about 12,000 years ago. Is what we perceive as climate change an early stage in the next major solar event? It's the first question. The relatively moderate Carrington event in 1859 disabled world telegraph systems and lit the skies with auroras for several days. An event of the same magnitude today would likely knock out proportions of the electrical grid, hydroelectric systems, satellite communication, GPS, and unprotected surface electronics. Are you factoring space weather plasma into your model?
Okay, so I'll answer by saying, first of all, that I'm not a modeler. So I don't prepare these models, and I'm not intimately familiar with the solar radiation that you're talking about, the electromagnetic components. But I will say, I think we saw this in the diagram, in the slides, that we know that on long time scales, thousands of years, the first and foremost process that controls climate on Earth is solar insolation, basically the sun. How warm is the sun? We can factor in additional components such as carbon dioxide and the electromagnetic, I forget the word, radiation or processes, which I'm not familiar with. I don't know if the IPCC, how much of it, of that component is considered by the IPCC models, but I will say that it's probably a component that we need to take into account, but it's not, I think, related to what we see over the last 100 years, this boost, this explosion of temperatures and carbon dioxide, and it's probably a secondary component in dictating future climate. So I didn't give a good answer here, but I want to emphasize that there are many small processes that take place. Many small processes or non-small processes that impact climate, and it's a really, really complicated thing to wrap our heads around. Climate models are really difficult to prepare and run. So, you know, maybe it has a role and maybe it doesn't.
Okay, I'll take a couple more questions here and just given the time. What is the prediction for the next glacier period? Are the lake's precipitation trend represent an important tool for this prediction and maybe climate change? Did I read that right? Does that make sense?
Yeah, okay, so that's a great question. Let me just turn back to one of my slides, okay. So based on what we understand from solar insolation and past patterns of climate change, we today, okay, at time 0 on this diagram, we today should actually have shifted back into a glacial stage. So in fact, we're not supposed to be in this warm climate which we're in right now. And we, as a scientific community, don't really understand why this has not happened. And whatever happened over the last 100 years, that didn't cause us not to slide back into the glacial. But it might have a role in it. People have suggested that over the last 5,000 years, human activity did kick in. Agriculture, production of carbon dioxide on a low level, far lower than whatever we see over the last 100 years. But that might have played a role in shifting the game and providing a positive feedback, which is inhibiting our slide back into a glacial. Maybe not. We don't really know the answer to that, but it's a good question to ask. So when will we slide back into a glacial? We should have already. Why haven't we? Open for discussion.
Okay, great. I just want to say before I take the next question, this recording will be available, and we will make that available to everyone. And I will talk to Adi about making his PowerPoint presentation available if he's comfortable with that too.
Okay.
So we'll let you know. Last question. Assuming that the recent dramatic increase in the CO2 levels is real, would you consider it due to human or solar or volcanic activity?
Okay, so again, looking at the slides, looking at the data, and you can all look for yourselves online, this is all open data, it's real. There's no question about whether carbon dioxide is real or is it fake news. It's real. We measure it all the time. It's there. What causes this and whether it's human related or not, again, I have a really clear opinion about this, but you can judge for yourselves. I mean, if you look at the long-term natural variability of climate and go back to those slides, you can see that the last 100,000 years are completely out of context, out of scale. They're completely not part of the natural cycle. My conclusion here, mine and of course the larger scientific community, is that this shift in temperatures, which goes along with carbon dioxide concentrations increase, this is related to the Industrial Revolution and human activity over the last 100 years. So to the best of our ability as scientists to use observations and make some interpretation and conclude something about the processes that take place here, this is our answer. Carbon dioxide increases and global warming, as documented over the last 100 years, is real and associated with human activity.
Great. Well, not great, but thank you for the answer. Hopefully, us quarantining over the last 6 weeks, I've kind of heard that there has been decreases in pollution and some environmental advantages. Is that true?
So that's a really, this is a great experiment for scientists, because suddenly we're in one situation, and then we have an opportunity to examine, close off the tap of humans and just examine the natural system. So there's good news and bad news, okay? First of all, we're still in it, so I don't think we have many conclusions at this point. But a similar thing, unfortunately, happened after 9/11, when for a few days, everything shut down. And let's think about today. So pollution, of course, is going down. There's far less emissions and human activity is down. And this causes the atmosphere maybe to clean up. And we see this in some cities. There are many, I might even have a slide, let me look it up. We see that the measured pollution on the right-hand side here, you can see France a year ago and today. So the measured values are lower. But this also, and this is good on the long term, but on the short term, the less particles we have in the atmosphere, whether we consider them pollutants or not, the less particles we have in the atmosphere, the more the radiation of the sun onto Earth is efficient, is intense. So temperatures could actually, following this change in human activity, temperatures could actually jump up a bit. I haven't seen data for the current event, but I know this happened after 9/11. So it can go both ways. Of course, on the long term, environmentally speaking, the decrease in human activity is good. Less pollution, less consumption, okay? We consume less, we need less gas for trucks to deliver products, and so on and so on. On the left-hand side, you can see the concentrations of nitrogen dioxide, a pollutant, in the atmosphere over several cities. And it's only in Los Angeles where we see a clear decrease in concentrations. In other places, it's a maybe. And it's a maybe because the atmosphere is a big thing that moves around quickly. So we want to be looking at the global picture, and that I haven't seen data for that yet, but it would be interesting to wait and see it.
Interesting. Thank you, Adi. This is great. We're so glad that you were able to join us today and to share some of your work and your findings. We greatly appreciate it. To those of you still on, thank you for attending. Please visit afhu.org for future webinars. Stay safe, be well, and take care. Thank you.
Thank you all.
Take care.